When doing any analysis of this kind with data, whether it goes into a machine learning model or an AI system, if it is based on data, we should ideally spend some amount of time investigating the data. We've done some pre-processing on it just to make sure that we understand the data types and check for missing values and all of that, duplicate rows, etc. And we can go through an exploratory data analysis exercise here as we can do in any analysis. So one way to do that is to visualize the data. And let's take a look at defining features. So when we look at data and we say, I'm going to select certain variables. What kinds of variables? Those where the data type is number. Why am I doing this? Because I want to make sure that I do my EDA only for things that make sense. In this case, numbers. So with this code, what we will get is we will get plots. And the plots will tell us what the data is like. What are these plots telling us? They're telling us the summary statistics through a histogram. A histogram simply tells us what is the distribution of these variables, both from the perspective of central tendency as well as from the spread. Note that what we are looking for is a relationship between sales and other variables. This isn't giving us that. It is giving us a univariate summary. There are some situations where we worry about things like, is the data normally distributed or not? For now, let's not worry about those things. We'll keep it simple. These are parts of what we discussed as, or what are typically discussed as, the assumptions of linear regression. And we've been proceeding under the assumption that the assumptions are valid. So we can keep doing these plots in a variety of ways to get a variety of inputs into the data. Instead of histograms, we can look at box plots, much the same way as you're seeing for other variables. What's the new kind of input to the learning process that a box plot can give you, that a histogram perhaps cannot or is not equipped to, is to look at skewness and to look at possibly outliers, individual points that may bother you. These are important in regression analysis in two distinct ways. One is they may turn the line in ways that are not desirable. They may, in some way, introduce a bias into your prediction. The second is they might have too much of an influence in the regression line. And in more advanced uses of regression, these become crucial points to see. And they're particularly crucial if the data set is small. 3000 is a moderate sized data set, but for small data sets, individual observations, either as outliers or as influential observations, influential to building the model, too influential perhaps, need to be looked at. But less of a problem if you've got a very large data set, the impact of individual observations. We can continue doing these plots, investigating different aspects of the data set. Like I said, I don't want to focus too much on these, but they do give some insight on different kinds of variables. Remember, there were two variables for which we did not have, shall we say, histogram. Why not? Because they were categorical variables, region and popularity. So here a histogram may not necessarily make sense in the conventional way, but a variant of it that's called a count plot, which simply counts how many of these variables or how many of these observations are in each of these categories. How many do we have in each region and how many do we have in the popularity variable as well? Is that device popular within that row? Think of it as, say, a region. Think of not a region, because region is a variable here. Think of it as a store. Is it a very popular product in that store? Maybe that's what this variable, popularity variable, is picking up. So now we have ways through histograms, through count plots, bar plots, if you want to use another term for them, to summarize data. This is not very helpful for solving the particular problem that we have. Let's keep our focus on the problem that we have, which is to model sales and the other variables. By looking at variables one at a time, we're not progressing in that direction. So to progress in that direction, we need to look at variables at least two at a time. And one of those two variables that we are looking at should be sales, because we want to know how does sales depend on other variables. An easy way of doing that would be by doing a pairs plot. And you can see a pairs plot here. So let me run this. This may take a little bit of time to run. We now have our pairs plot. Our numerical variables are now plotted one against the other. And all of them are. There are 8 of them in the data set. But the one that we are interested in, let's go down and see that. So we are interested in the last row of this pairs plot. What is this last row telling me? It has on the y-axis sales and on the x-axis all the other variables. Advertising, engagement score, discount percentage, customer ratings, price, return rate, length of product description. The last is the histogram. These plots tell me how each individual numerical variable potentially impacts sales. And as you can see, there's some signal there. For example, sales seems to be positively correlated with, say, advertising expenditure. What does positive correlation mean? It means that as advertising expenditure goes up, sales is going up in a statistical sense. Not all the time, not for all the stores, but by and large, your advertising goes up, sales tends to go up. And this may be true for customer engagement store as well. These are places where the correlation is positive, which seems to indicate that I should be able to get a regression with positive slope here as well. Some of these seem to indicate a negative correlation, for example, product price. Once again, you may look at this plot and say, but this doesn't look like a strong negative relationship. And you may be right. We are not commenting on how strong the regression is or how good it is. We'll get to that. For now, we're simply trying to get a sense of which variables I might want to begin my analysis with. There are 2 styles in which data analysis with many variables is done. One is what I might call forward inclusion. What that means is begin with nothing and keep introducing variables into the model. And the other is what I might call backward elimination, which means begin with everything and start removing variables that we feel does not make sense. The simple regression point of view suggests that we do the forward inclusion approach and say, if I want to build this really simple model, which are the ones that I should be looking at? And a plot like this gives me some indication of that. Now, this is a visual indication. Can I actually find those correlations? Yes, I can. I can, in fact, even visualize what those correlations are by doing a heat map. Now, what is a heat map? If I do data.core, which you can see here, I get the correlation numbers. The correlation numbers associated with data as a data frame can be visualized within Seaborn, which I had abbreviated as SNS when I imported it, as heat map. And now all the numbers that the correlation returns can be visualized through colors. Let's see what those colors are, and you can change the color code if you wish. And the heat map now tells you that indeed there are some correlations. Ignore the diagonal. Ignore the diagonal. Think about why. Because what does the diagonal mean? The diagonal means that this is the correlation between a variable and itself. So advertising, which is the first row and first column, correlates with advertising. It's the same variable, and that correlation is 1. If I plot advertising versus itself, I get a straight line. Nothing interesting about it. And the correlation is 1. So for a matrix like this, or for a heat map like this, the diagonal is 1. What about other correlations? Let's, for example, look at the correlation that we were interested in. The correlation between sales and advertising. The correlation between sales and advertising is 0.64. 2 comments. Number 1, it's a positive number, reflecting this positive correlation that we saw in the plot, sales and advertising. Second, it is neither 0 nor +1. It's somewhere in between. +1 would have meant that is perfectly correlated. It is not. It means there is a positive association between advertising and sales, and 0.64 is not a small correlation. Seems instinctively and intuitively a correlation we should look at. Let's see if there's a negative correlation corresponding to price, which is also something we saw in the graph, and that is minus 0.16, which again is negative, but as we have seen in the plot, not as strong. The signal in the, shall we say, driver of sales of price seems to be weaker than in advertising. Yes, advertising increase relates to sales and in a stronger way than sales relates to price. We're going to make more sense of these statements, but you're already getting them from the numbers. 0.64 on the positive side for advertising and minus 0.16 on the negative side for price. So, of course, in the notebook, you can record all of these. It's a good practice to do that so that when you use it again, you'll know what your findings were. And we see the positive correlation, the negative correlation. We saw the negative correlation with return rate as well, etc. And we might want to take, shall we say, advantage of these. Correlations make sense, however, only for numerical variables. Numerical variable, sales is a numerical variable, advertising is a numerical variable as well. How do we understand whether a categorical variable is a good predictor of sales? We can't calculate correlations. It doesn't make sense. But we can do other things. So, for example, we can see a box plot. And in this case, we see what's called a bivariate box plot. This is a box plot, Seaborn again, box plot, but I'm not doing it just on sales. I'm not just saying box plot sales. I am saying X and Y. Y is what I want the box plot for, and X should be, if I do this correctly, a categorical variable, a qualitative variable, which tells me how many box plots do you want to see sales for, if it is present. So this allows me to see whether popularity has an effect on sales or not. Now, this is not quantifiable. How is this being arranged? Not necessarily in a way that I can quantify and saying, okay, as popularity increases, sales increases, or as popularity decreases, if I go from left to right, sales decreases. I can, but not in a numerically quantifiable way. But it still tells me you should perhaps include popularity somehow in your model, because it does appear that when popularity is low, I'm not doing too well in terms of sales, or I'm doing worse than expected. Lower sales for unpopular products. I can do the same thing for regions as well. But for regions, maybe I'm not seeing as much of a difference. And maybe this variable is not that important to factor into my sales prediction equation.